We're now continuing with the review for the midterm exam. We're ready now for problem 22. So let me pull that up here. So this problem involves something called the difference quotient. You see over here, there's a table here, and you see this little expression here. Now, let me try and just do a very quick summary of what's going on here. So we're given this function, f of x equals x squared. And we have this table here, although the first thing they ask us for, they ask us to simplify to figure out what this little expression would equal. So let's go and do this first, because this is really a problem of just understanding function notation. So we're going to get to this table in a little bit, but right now let's just do this, where we're given a function, f of x equals x squared, and we're asked to determine this expression, f of x plus h minus f of x over h. And this is a special expression called the difference quotient. So let me write down on my paper the information for this first part of this problem, and we can work it out. So here's the function we're given, and they want us to calculate this thing called the difference quotient, which is a very famous expression that I'll explain in a minute why this actual expression is so important, oftentimes called the difference quotient. So we got three things going on here. We have f of x plus h minus f of x, and all that divided by h. So I want to apply this to this function x squared. So let's first figure out what f of x plus h would equal. So the first part of my expression. F of x plus h, you know, in function notation says, here's my function. Every place I have an x in my function, I want to replace it with x plus h. So therefore, since it's f of x equals x squared, f of x plus h would be, I replace the x with x plus h. So f of x plus h equals x plus h squared. And I'm going to go ahead and multiply out, just in case you've forgotten, x plus h squared means x plus h times x plus h. Now, if you FOIL this, whatever you like to do to multiply it out, when you get all done, you end up with x squared plus 2xh plus h squared. So f of x plus h equals this. So that's going to be the first part of this expression. Now, really, I can go ahead and figure this out because this is really the hard part. The rest of it, it's just a matter of plugging things in. So let's write out this difference quotient, and I'm going to start plugging in what I know and see what happens. So f of x plus h is this right here. So it's x squared plus 2xh plus h squared. So that right there is the f of x plus h. Minus f of x. Well, f of x is just my original function, right? Which is x squared. So I just put in minus x squared over, and I leave the h. So this is now my difference function for x squared. Now I should try and simplify this. If I look at the numerator, I've already got x squared plus 2, just to make it very clear here. So then this is f of x. But if I simplify it, I have x squared plus 2xh plus h squared minus x squared. Now, x squared minus x squared, those are like terms. I can combine those. As a matter of fact, they cancel out. So what I'm left with is just 2xh plus h squared over h. Now, actually, I can do some more simplifying. Some of you already know how to do this, and you can see it right away because I have an h in this term, an h in this term, and an h down here, so I can cancel out an h. If you can't quite see that, what if in the top I would factor out an h and create these parentheses? Then hopefully you can see how these h's would cancel. So whether you do it here or here, in effect, when it's all said and done, we're left with 2x plus h. So in a sense, this is now the simplified difference quotient. So I should go back to the problem now and plug that in as my answer. I'm an engineer by training, so when things aren't straight, it sort of bugs me. It's just one of my pet peeves. All right, so I think right here, I'm going to plug in 2x plus h. Okay, so that first step was taking this function and calculating the difference quotient. Now, what we're going to do is we're going to fill in this table. And of course, this last column is the difference quotient, which is actually this little equation here. So I'm going to take 2x plus h and calculate it for each of these right here. So let me write down that information, and then we'll do it in a minute. But I actually want to take a minute and sort of explain briefly to you why we're even doing this or what the purpose of it is. So let me write down all right. So let me go back to, so here's the table. And we're going to calculate this in a minute. It's pretty simple because here's the equation I'm going to use for my difference quotient. I'm just going to calculate it. But before I do that, let me just take a minute, and hopefully you've already learned this and you've gone over this in the book, and maybe you watched a video, or what in the world is going on with this difference quotient. So let me take a minute and try and explain to you. What I'll do is, let's go ahead, this problem, we're looking at a function f of x equals x squared. I'm going to try and draw graph out this function just to explain what we're doing. So here's 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. So this is like 1, and this is like 2, 3, 4, 5, 6, 7, 8, 9, 10, up to 15. If I were to plot this, okay, so when x is 0, the function is 0. When x is 1, the function is 1. When x is 2, 2 squared is 4, the function is 4. When f is 3, it's like 9. When x is 4, it's like 16. Now I can do the same thing for the negative values of x. Negative 1 gives me 1. Negative 2 gives me 4. Negative 3 gives me 9. Negative 4 gives me 16. So if you graph it, this is actually a parabola. Pretty common function in math. But here is now this difference quotient. Now the thing that you have to understand that is whole key to this part of calculus, this whole difference quotient is actually a way to calculate the slope at any point on this curve, right? And in this case, we're looking at a specific point on this curve when x is 4. So we go up to here, and basically we're asking ourselves, what's the slope of this curve at x equals 4, which is this point right here. Now, when you have a curve, the way we think about the slope is we have this, what's called this tangent line, right? You've been studying about these tangent lines. So really, the slope at this point where x is 4 is really the slope of this tangent line. And you know what this difference quotient is? This difference quotient is an estimate, a way to try and calculate the slope of the tangent line. Now, I don't want to take time now to go into what the h's and all that stuff means, except I'll say this. The principle is, as h gets to be a smaller and smaller number, this calculation begins to approach and becomes closer to the actual slope. So the bottom line is, the problem we're working, we're given this function, and they're saying we're going to figure out the difference quotient for this function at one specific point on the graph when x is 4. And the way we find the slope at that point is we use this difference quotient. You notice the x here, the x doesn't change because we're looking at the point when x is 4. What changes is the h. It gets smaller and smaller because the smaller the h gets, the more accurate this difference quotient becomes, because this thing is really an estimate of the slope. Now for us, we've determined that this difference quotient for our problem is 2x plus h. So I go down here, when x is 4, h is 2, I plug in 4 for x, 2 for h. The difference quotient is 10. So I'm saying with an h of 2, my estimate for the slope when x is 4 is 10. However, let's see what happens when I make h smaller. So now if x is 4 and h is 1, I plug 4 in for x, I plug 1 in for h. 2 times 4 is 8 plus 1, it's 9. So now the slope has changed from 10 to 9 as h gets smaller. Now what happens as h goes from 1 to 0.1? It gets a lot smaller. So I plug in 4 for h, I plug in 0.1 for h, and I end up with 8.1. So once again, it looks like the slope, my estimate, keeps dropping. And finally, if I do the same thing where x is h and h is really small, 0.01, this thing ends up equaling 8.01. Now what's going to happen is, as h gets smaller and smaller and smaller, I mean, I could have, the problem doesn't have this. If I had made h really small, then this would be 8.001. And the idea is, as h gets smaller, this difference quotient, which is the slope, gets very close to a number. And whatever number this thing gets very close to, in a sense, that's going to be the slope. So you can see it starts out at 10, it goes to 9, 8.1, 8.01, 8.001. What is this thing sort of getting closer to? It's getting closer to 8. You know what that means really? For this function at x equals 4, we're going to say the slope is going to be 8. That's what we're trying to show here. This difference quotient is a way to calculate the slope at a certain x and h. And as h gets smaller, this calculation becomes a more accurate number for the slope, and we can see that it's 8. So let's go back to the problem, and I'm going to plug in the values for this table. Hopefully I did all these calculations correctly. So you can see how for 4 and 2, I had 10. For 4 and 1, I had 9. For 4 and 0.1, I had 8.1. And then 8.01. So I'm going to check, and hopefully those are all correct. All right, so that was that problem. Now this next problem is sort of similar in a sense that they've given us now this function, p of x, looks pretty messy. Actually, this is like a story problem. The average price of a ticket to a baseball game can be approximated by p of x equals, where x is the number of years after 1991 and p of x is in dollars. So what they're trying to do is they're trying to sort of work up an equation that tells you how much a ticket costs according to what year you bought the ticket in. So like most things, I assume that the prices of tickets kept increasing as time went on, and they've come up with this equation that sort of predicts or tells you how much the ticket prices were according to what year you were in. So they're going to start at 1991, and basically if you plug in the year into here, you can see how much tickets cost. Now what they're going to do is they're deciding, hey, let's look at specifically, let's look at the ticket price when x is 5. That means 5 years after 1991. So basically p of 5 means, let's look at the ticket price for the year 1996. And then they say, what's p of 15? That means we're looking at 15 years after 1991. So now we're going to calculate the ticket price in basically 2006. And then they say, hey, so how much did the prices of the tickets change? What was the price of the ticket in 2006? Subtract the price of the ticket in 1996. So how much did the price change in those 10 years? And then this last thing is called an average, where you say, okay, how much did the price change and how many years changed? And this tells you how much, basically on the average, how much the ticket price changed every year. So let me write down this information and go ahead and do it. This is not a hard problem. It's just a lot of math. I would definitely have to use my calculator for this one. This is sort of a messy equation. So this is 23. So P of X is 0.03 x squared plus 0.44x plus 8.05. And they first want P of 5, and then they want P of 15, and then they want P of 15 minus P of 5, and then they want P of 15 minus P of 5 over 15 minus 5. All right, let's work this problem out. So once again, starting year is 1991. So basically for 1991, that's when X is 0. That's like when you start counting. So therefore P of 5 basically would mean the ticket price after 5 years, which is 1996. So P of 5 means I'm going to plug in 5 for X into this equation, see what it equals. So 5 squared, so it's going to be 25 times 0.03, which is 0.75 plus 0.44 times 5, which is 2.2 plus 8.05. So when I add these together, so basically what this equation tells me is in 1996, we paid $11 per ticket. Now they say, well, how about looking at the price after 15 years? So this is like 2006. So you do the same thing, except you plug in 15 for X up here. So 15 squared times 0.03. It's like 6.75. 0.44 times 15. 6.6 plus 8.05. So then add these three together. Wow, in 10 years, pretty big jump. 1996, the ticket cost $11. And in 2006, the ticket cost $21.40. The third question is, okay, so what was the increase in the ticket price for those 10 years? So you take 2140 minus 11. I think I can do this in my head. Looks like for those 10 years, the ticket prices went up by $10.40. So that's how much the price of the ticket increased. And then the last thing they do is, okay, so since that happened over 10 years, what's an estimate of how much it changed per year? So you take what we just calculated, the change in the ticket price, and you divide it by the number of years you're looking at. We already calculated this to be 10.40, and that increase was over 10 years. So you say, so just for fun, if we assumed that it was the same, the price changed the same every year, which it probably didn't, but it's just an estimate. How much did it change per year? Well, basically every year the ticket price went up $1.04. So therefore, after 10 years, it ends up going up almost $10. So not super complicated. So let me go back to the problem. I'll plug in my numbers, and I hope I did the math correctly. We'll find out when I plug these in. So I said P of 5 is 11. That's good. P of 15, I said was 2140. That's good. Now the difference should be, whoops, 10.4. And then the average, where you take the difference divided by the number of years, should be 1.04. So this kind of problem is called like the average rate of change. Now, ask a question. Which of the following is the appropriate interpretation of the result? The result A says the result tells us the price of baseball is more than, the result tells us the price of a baseball ticket is, B is from 19 by this amount per year. Wow. Let me figure out which one is correct. Let's look at D. This amount was the average price difference of a baseball ticket. The average price difference of a baseball ticket. No, because we're doing it on a per year thing. From 1996 to 2006, the price of baseball tickets increased by this amount per year. Not really, because this is an average. The average price for a ticket increased on average by this amount. I think it's this one because it's an average. I won't lose too much sleep over this last one. This is sort of confusing. All right. All right. I think this video has gone sort of long. Let me stop now, and we're going to pick it up with problem 24. And now you see here, we're back to the difference quotient, but now it's a little different because we're taking the limit of the difference quotient. So we'll briefly talk about that when we start the next video.